So today we are going to do Dirac delta function. I've already started this topic in the series of quantum mechanics, and as we go along, we'll see how important this particular topic is. Since yesterday, not many people have joined the class, so I'll go with a sense of a revision at first. So what is Dirac delta function? So Dirac delta function is a function is in general is it's not a function, or rather it's a distribution. First thing that you should be understanding is it's a distribution. Okay, and as we go along, we'll see how ubiquitous it is to physics. Especially, you will see its application. Sorry. Okay, so it's quite ubiquitous to physics, especially in your quantum mechanics, statistical physics, electromagnetic theory, even classical physics. You'll find that not many times you'll be seeing this function delta function. And a slight motivation you can get is a slight motivation you can think of it is in the manner. Let's say if I'm saying that I have to tell about the volume of the point charge. So if I have to tell about the volume of the point charge, I need a certain mathematical representation, and it becomes very impending for us to very necessary for us to have an idea of this. So, for example, if I have to write a if I have to write a volume charge density of a point mass or point charge, so volume charge density of a point charge or point mass, I would definitely need a function like this. And let us see how it becomes indispensable. So, for example, if I have a point charge located at x equal to 0, that is at origin, if I have a charge q, and if I say what is the charge density of this particular charge, so this is a point charge. If I say a point charge, its volume should be trivially 0. It cannot be even anything. Okay, it cannot be even anything. Like you cannot define a volume of a point, right? So how one could justify any well-behaved function to define the volume charge density of a charge? Okay, so this is a kind of motivation that I'm giving you right now, because this is something that you already know. So that is why. So for example, if I say what is the volume charge density of a point charge, now you are in a fix because it is a point charge. So volume should be equal to 0. It cannot be even tending to 0. Okay, so you can see that whenever you have this kind of situations where you have some point mass, point charge, or otherwise otherwise a function which happens to be at a point and does not happen to is actually 0 for all other points, you will be frequently encountered by such kind of uh, uh, like distribution that is called as Dirac delta function. So let us think upon it. So for example, if I'm supposed to write the volume charge density of charge q, in any case, even if I take del q upon del v, and even as del v tends to 0, this is not even the ideal case, because for point charge your volume should be ideally 0. But let's say if I had just come as close as to the realization, I would come to a conclusion that where the point charge q is located, my rho should be tending to infinity. You can see. Say for example, my charge is at 0, and if I say that at this particular point, define me the volume charge density, you would say the volume charge density is infinite, because see, at this particular point, because since it is a point, del V tending to 0, overall this quantity will become very large, as possible. I'm not saying that this is a complete the true situation. It is not the complete true situation, because for a point charge, you cannot expect even a single infinitesimal volume also. So just close to idealization, if you think that what would be the volume charge density of a point charge, it should be ideally infinite. Okay. Now this is an infinite contribution here. And since point charge lies on 0, otherwise it is not lying anywhere else. So it will be 0 everywhere. So this is a kind of thing that you are expecting. So this is a kind of thing you are expecting, and which actually leads us to a definition of Dirac delta function. Okay, so you should understand these are weak functions in mathematics called sometimes. These are also called as distributions, also called as generalized functions. And there is an elaborate theory of generalized function that I may address in a different lecture altogether. But as of now, you are going to just see what more what we can take sort of motivation to do physics. Okay, so all these functions like Green's function or probably the Dirac delta function, they come into the category of these. What are these? We'll address them later. Okay, we'll address them later in a different lecture altogether, because it will become all the more very rigorous, and probably we'll be deflecting away from our main agenda. So that's why I'm not going there. Just try to understand. By an example, I'm trying making you understand that if I am supposed to write a volume of a point charge, how would I be able to do so? Because see, it is a point charge. It cannot have any dimension. Since a point charge ideally should have a volume 0. So if in case I just try to write dq upon dv and dv as small as possible, I would be able to say that at charge at x equal to 0, where your point charge is located, your volume charge density should have an infinite contribution, and otherwise it should not have any contribution. So such functions, such particular description can be encapsulated in the form of the Dirac delta function. And I've already told you it is very, you can see in advanced physics, like in quantum mechanics or in statistical physics or classical or electromagnetic theory, you will find several instances where you will be finding this kind of function. As simple as completeness of wave function, also you'll find Dirac delta function. In Liebniz theorem in statistical mechanics, you'll find it as an impulse force. You'll find in classical mechanics, point charge description in electromagnetic theory, and so on and so forth. You'll find that you'll find it many a times, this particular thing, or probably relevant integral representations to Dirac delta functions would occur in your further course as I teach you. Okay, so therefore I feel that this is quite important, and that is why I'm writing it. So okay, so how would Dirac delta function be defined? So at x equal to 0, it is having an infinite contribution, and for all x not equal to 0, it is having 0 contribution. You can take, I'm saying contribution, you can say that is, you can also say it as a distribution. So entire distribution of whatever physical quantity relevant, let's, for example, if I'm saying charge, the volume charge density would entirely be at x equal to 0. Otherwise, it is nowhere to be seen. So entire distribution is at x equal to 0, and that entire distribution is infinitely large. So this is one. And secondly, aided with the condition that this area under the spike should be at unity. So area under the spike should be unity. So these two conditions, when written together, form the definition of the Dirac delta function. So what is Dirac delta function? The Dirac delta function suggests you that at a point you have an infinite contribution, and beyond that particular point you have 0 contribution. Okay, and with an extra condition that this particular integral under this area, under the spike, or you can say the area under spike, should be equal to 1. So these two conditions formulate the definition of what you call as Dirac delta function. Let's say if I shifted my origin, and let's say if my charge or whatever point quantity I'm interested in is at, let's say, x equal to a, then there will be an infinite contribution at x equal to a and 0 contribution for all x not equal to a. And again, minus infinite to infinite, Dirac of x minus a dx would be equals to what? 1. Are you getting my point, or is there any confusion? If there is any confusion, do let me know. So this is something that I've already taught yesterday, but still, because people were not there, so I'm just trying to repeat it all over. Is there any confusion till now? Nobody saying anything. Is that audible? समझ गए क्या? पूजा समझ में आया?
नहीं भैया, कोई प्रॉब्लम नहीं।
मोहित को समझ में आया? अल्पना को समझ में आया?
भैया
हाँ
भैया थोड़ा सा रिपीट कर दीजिए ना, कहाँ से स्टार्ट किया है? मुझे अभी जस्ट ज्वाइन किया है मैंने।
हाँ 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 ठीक है. सो हम लोग क्या कर रहे हैं? वी आर स्टडिंग Dirac delta function. Okay, we are studying Dirac delta function. So for example, first thing you should understand, you'll find it at numerous instances in physics that you'll be facing this particular function and this particular construction. So that is why I'm starting with this kind of fundamental thing. Okay, now Dirac delta function का मतलब क्या है? पहली चीज, it's not a well-behaved function, so to say. So it's not a well-behaved function. Now, what do you say? What is a well-behaved function? I would say well-behaved function is one those you already know right now. That would be enough for me to say. For example, sine x, cosine x, exponential x, the trigonometric functions. These are all well-behaved functions. But this is not kind of well-behaved function. As we go to the theory of the generalized function, we'll know what are good functions, what are fairly good functions, and all those sort of technical things we'll do in the generalized function. But right now, just understand this is not a well-behaved function. As in, अगर मैं तुमसे कहूँ what is the volume of a point charge? Let's say what is the volume of a point charge? You will say volume of a point charge is 0. Okay. Now if I ask you what is the charge density of a point charge? Now you are in a fix. Because charge density, if at all you have to write dq upon dv, or simply if it's a uniform case, then you have to write q over v. Now, if I'm saying this is a point charge, it does not have a volume, this will give you a result which cannot be represented by any of the functions that you have till now studied. So q by 0 is nothing. I mean, it is not defined. But what if I have to somehow represent this particular function? So I would say, let's say I would say this q is entirely located x equal to 0. So even if I go infinitesimal small volume, as small as possible, so this particular thing would go towards infinity. It implies if I have to write a volume charge density of a point charge, it is to have an infinite value at a point where your charge is located, and otherwise it should not have any value. Is that clear? मैं कह रहा हूँ कि अगर एक चार्ज q कहीं पे located है, let's say x equal to 0 पे, और मैं कहूँ इसकी volume density लिखो, तो you will say okay, it will be having some very infinite kind of distribution at exact x equal to 0, and otherwise, because since charge is located at x equal to 0, it cannot be located anywhere else. Is that clear to you? So such kind of representations where you have an infinite contribution at a point and zero contribution for all other points, this is encapsulated in form of Dirac delta function. So Dirac delta function give you an infinite contribution at a point where it is located, and this particular location of point you can understand by seeing the argument of the Dirac delta function. You see where the argument of the Dirac delta function is 0, you will have an infinite contribution, and where your argument is non-zero, you will have a 0 contribution. So let's say if I just modify the definition and place it at x equal to a, then it will be equals to what? It will be equals to infinite contribution at x equal to a, and it will be non-infinite contribution, or you can say 0 contribution at x not equal to a. Such definition is called as Dirac delta function, and these are what you lately come to know as generalized function. Right now, I'm not getting into all those things, all those trivialities, difficulties. Otherwise, it will become very difficult for you to understand. So right now, I'm more teaching you more so that you can remain motivated towards the physics side. Okay, are you getting my point? पूछा समझ में? मतलब एक जगह infinite contribution होगा और उसके अलावा कहीं पर भी जाओगे, you will have a 0 contribution. ऐसा कुछ function को Dirac delta function कहते हैं. With an extra condition कि अगर इसकी area under peak निकालोगे तो 1 आना चाहिए. What I'm trying to say कि spike होगा कहीं ना कहीं, और ये जो spike का जो area होना चाहिए, that should be equals to 1. So I'm saying that this particular area should be normalized to unity. So Dirac delta function means the area under spike should be normalized to unity. Is that clear to you? So these two definitions, in short, forms the definition of the Dirac delta function. Is that clear? I think it's clear. Now I'm moving forward. Okay. Now, the problem is that such kind of representations you don't see quite often in your physics course, in mathematics course, because in mathematics course of real functions, you'll find that functions where you have a division by 0 are not defined. Okay. So for example, if I say what is the value of 1 upon sine x if x is equal to n pi, you will simply say it does not exist. Okay. Because you see 1 upon 0 is not defined in real realm. So what is our idea? We'll try to represent our Dirac delta function in form of some suitable sequence of functions, or you can say limit of sequence of function. Limit of sequence of functions. So this is what I did yesterday also, but I'm going to do today also, because yesterday no one was there. So limit of sequence of function, or simply limit of some family of functions. Okay, so this is a sort of representation of Dirac delta function that I'm right now teaching. Because see, Dirac delta function as such, you've understood that it is having an entire distribution at a point, and otherwise there is no distribution. There is simply no distribution. Now, in order to just have a look at it, and just to know in terms of what we have already known, how would we represent our Dirac delta function? So there are many such distribution. There are many such functions or family of functions you will find in your in your books or everywhere else. But I'll cover a few of them. Okay. So the first one that I want to cover is a rectangular function, or you can say that I don't know with what name I should address it, but it is more often you'll find it in the Griffith's book also, like Griffith's electromagnetic theory book also. You'll find it on the second or third page number. So okay. And another suggestion is you just try to read Griffith. I mean, Griffith is a classical book on electromagnetic theory, but if you try to see that like whatever he writes in Dirac delta function in nutshell, that is good enough for a physical insight for you. Okay, so let us move along and see these functions. So first one of them is this. So how should I write? I'll write some rectangles. Okay. You can say sequence of rectangles. Okay. So you can say sequence of rectangles. Sequence of rectangles. So if I want to write a sequence of rectangle, see, another thing is, if I have to write a Dirac delta representation of a Dirac delta function, then I must be in a position to justify three things. One, there should be a peak at the desired location. Second, the area under that peak should come as zero. Area under the peak should come as zero. Should come as one. Sorry, and otherwise, when जहां पर भी peak located है, all other points, your function should give you a zero. Is that clear? मेरी बात समझ में आ रही है? मैं हिंदी में समझाऊं फिर वापस से?
Yes, babe.
देखो, मेरी बात समझने की कोशिश करो. अगर मैं ये कह रहा हूं कि मुझे डिराक डेल्टा फंक्शन को रिप्रेजेंट करना है इन टर्म्स ऑफ सब फंक्शन, ओके, इन टर्म्स ऑफ सम लिमिट ऑफ अ फंक्शन, व्हाट इज माय प्राइमरी रिक्वायरमेंट? माय प्राइमरी रिक्वायरमेंट वुड बी टू राइट अ फंक्शन व्हिच हैज अ पीक एट अ पॉइंट. ओके. Secondly, it should have a condition that the area under peak should be zero, and the third condition is that for all other points, where the peak is not there, your function should give you a zero. Okay. Now I'm saying if I'm writing this sequence of rectangles, okay, if I'm writing this sequence of rectangles, these sequence of rectangles should generate a peak. Point number one, the area under peak should be one, and third property should be that for all other points where your peak is located, your function should be zero. So let us first think about this particular function that I'm writing right now. Okay. So I think this is the function that you'll find in your Griffith text. You'll find some triangular thing also, if I correctly remember, if you just go through your Griffith book. Why I'm telling you Griffith? Because that has given sort of physical insight to this Dirac delta function in more appropriate sense. So that is why. Okay. Okay. So just try to see this particular function and try to construct it on your copy. Okay. So अगर तुम्हारे पास copy है, try to construct it. And please do sit every time with some copy. Otherwise, if you're just listening to me, it's not going to work out anyway. Okay. So I'm going to make some. These things. Okay. I don't know how to get this. एक मिनट दो यार. Okay. So देखो, ये function क्या कह रहा है? What does this function say? This function says कि it is equal to 0 if x is less than minus 1 upon 2n. So let me make somewhere minus 1 upon 2n. So I'm making it here somewhere minus 1 upon 2n, and I have here making 1 upon 2n. Okay. And if x lies between minus 1 upon 2 and 1 upon 2n, it is equals to n. So I'm just marking it somewhere here. So if I say my n is equal to 1, so it means that my function would be equals to 1 when my x lies between minus 1 by 2 to plus 1 by 2. As I keep on increasing my n, let's say now I keep n equal to 2. So my the width of this interval would become minus 1 by 4 to plus 1 by 4, and the height would become 2. Is that clear? If I take n equal to 3, then it will be minus 1 by 6 to plus 1 by 6, and my height would become 3. And so you can see that as you are progressing, as n tends to infinity, this progression is taking you to a peak sort of thing, isn't it? You'll see that as you move along, as n tends to infinity, there would be a spike, a narrower spike at x equal to 0, and for all other points, it will be 0. So at x equal to 0, you will find that there is a narrower spike as n tends to infinity, and otherwise, also understand this is not the ideal Dirac delta function. This is only a sort of you can say representation. So you may say that even as n tends to infinity, there would be some width. Yes, there would be some width. Ideally, Dirac delta function will not even have a width. Okay, ideally it will not even have a width. So this is a kind of representation of the Dirac delta function in terms of limit of sequence of some functions which we already know. Okay, so as you move along, as n tends to infinity, you can see that your x is approaching 0, isn't it? As n tends to infinity, this is approaching 0, this is approaching 0, and this is tending to infinity. Can you understand this particular point? You see, as n tends to infinity, this is going towards infinity. As n tends to infinity, you are approaching 0 from the right hand side. As n tends to infinity, you are approaching 0 from the left hand side. And in those all of these approaches, your function should be 0. You can see this clearly. As n tends to infinity, this is x less than 0. And in particular, this is 0 minus. That is, you are to the negative of 0. And x greater than 1 upon 2n, as n tends to infinity, you are on the right hand side of 0. So if you go towards the right hand side, it is 0. If you go on the left hand side, it is 0. And as n tends to infinity, this particular thing goes towards 0. And n tends to infinity means here it will be infinite, so you have an infinite contribution. So this particular sequence of rectangles in the limiting case defines you something like Dirac delta function. Is that clear to you? Or should I repeat it all over again? ये समझ में आया नहीं आया? कोई बोल कुछ नहीं रहा है, वापस पूछना पड़ेगा। जो समझ में आया?
यस भैया।
अल्पना को आया?
हाँ भैया।
मोहित को आया?
क्या
है ना? ये हाँ बोलने का क्या लोगे, मतलब कोई पैसे लगते हैं क्या तुम्हें हाँ बोलने के? सब अंदर वहां गूंगे हो जाते हो थोड़ी देर के लिए। अभी मुझे समझ नहीं आएगा कि क्या करना आगे, फिर दिक्कत आएगी तुमको। प्लीज बोल दिया करो, अगर मैं बोलूं हाँ ना तब भी साइलेंट क्यों रहते हो? देखो मेरी बात समझने की कोशिश करो। इसके बाद लेट अस सी, अगर इसका मैं रेक्टेंगल का एरिया बताने की कोशिश करूं, इवन एज n टेंड्स टू इन्फिनिटी, this is minus 1 upon 2n, this is 1 upon 2, sorry, this is minus 1 upon 2n, this is plus 1 upon 2n. What is the width? The width is minus 1 upon n. घटा के देख लो, the width will come as minus 1 upon n, and the height is n. And what will be the area under this particular spike? This will be n into 1 upon n. आ गया 1. So even as n tends to infinity, your area under this spike would come as 1. This is the condition for Dirac delta function, yes or no? Dirac delta function क्या कहता है? You should have an infinite contribution at a point and zero contribution for all other points other than 0. And further, the area under that spike should come as 1. Okay. Now, if I have replaced it by some sequence of rectangle and I'm trying to find the limits of the sequence of that rectangles, I'm finding that this sequence of rectangles in the limiting case behave as if it is a Dirac delta function. Further, I'm also seeing that this area under the spike is 1. Is that clear to you? So this is how you realize your Dirac delta function. In some functions, so to say, your conventional functions, in terms of limiting case of some conventional functions or limiting case of sequence of some conventional functions. So let us move ahead and take a few more examples. Okay. Now you will say that how these particular points will be helpful to you. You will, as you progress in this particular lecture, you will be able to find the motivation as well. Don't worry about that motivation. Okay. Okay, so now let us take another case, and that would be you can take it as, let's say, only a positive rectangular pulse. So if you just take a positive rectangular pulse, so not a negative one. So here you had both positive and negative one. Now let us just see how to represent your Dirac delta function if you have only a positive rectangular pulse. So let's say if I'm saying this is a kind of definition I'm following, right? So function says Dirac n x if x lies between 0 and n, and otherwise it is, sorry, not 0 to 1 by n, it is n, and otherwise it is 0. Now if I say okay, sorry. Okay, so this particular function, if you just try to write in this manner, or should I write in this manner? Okay, so this is that particular function that I'm writing right now. This is your that property I'm already not putting. Okay, so I'll come to this property later on. Otherwise, it will be a difficult thing for you. Let us develop a few more things at first, and then we'll come back to the property and do all these things. Okay, just give me a minute. I cannot shift it. let me delete it. I'll come to it again. Okay, इसको मैं तुम्हें property पढ़ा के बताऊँ. Otherwise, it would be difficult to think. Okay, so let us take a few more example. And the second example you can take like a sequence of a Gaussian. Second example that you can take is, I'll come to that. Don't worry. Probably that requires me a property and of Dirac delta function itself. So I'm not going there. I'll do it. Okay. So next family of functions which I'm interested in is sequence of Gaussian. And let's say if I define my sequence of Gaussian as this, I think n upon root over pi, and then you should have e की power minus n square x square. This also I've discussed yesterday. Now let us think about this particular function. Let us think about this particular function at first. So you clearly remember, if I'm not, if even if you're a BSc student, you must be familiar with this Gaussian function. Quite many times you'll find this kind of function, and see how it is constructed. Okay, I should have made it quite broad. Okay, but otherwise yes. Okay, I should make it somewhat broad. Otherwise you get confused. But chalo, एक बार को रहने देते हैं थोड़ा सा. इसका broad ही कर देते हैं because this will be, I don't know. Okay, we should take it as a broader case. I mean, थोड़ा सा broad होता है ना, because otherwise you will get confused between a Lorentzian and a Gaussian thing. Okay, so if it's kind of broad only, ठीक है. Okay, so देखो, let's say these are all family of Gaussians. I'm saying family of Gaussians. Now, as we take, now just try to understand my point. If I take x equal to 0, if I take what? X equal to 0, this will become 0. E की power 0 is 1. And n tends to infinity, your del n x tends to what point? Will let me know. पूजा बताओ क्या होगा बेटा? At x equal to 0, ये हो जाएगा 1. Is that clear? At x equal to 0, e की power 0 कितना होता है? 1 होता है. और n tends to infinity लो, क्या आ रहा है देखो? Infinite. देखो हम क्या कर रहे हैं? We are trying to find the limit of these functions. We are trying to find the limit of these functions. Now there are two cases. One case is if your x is 0, and one case is if your x is non-zero. Okay? ये sequence of Gaussians दिख रहे हैं? अब देखो मेरी बात समझने की कोशिश करो. Now let's say if I say x equal to 0, this is e की power 0. E की power 0 क्या होता है? 1. n tends to infinity पे ये कहाँ जा रहा है? Infinity जा रहा है कि नहीं जा रहा है?
Infinity.
And x अगर नॉन जीरो हो गया, x अगर नॉन जीरो हो गया, so यहाँ पे कुछ बचा रहेगा. There will be some positive quantity here. It is multiplied with n square and negative is there, and there is n also. And now try to find me the limit n tends to infinity. Now if x is non-zero, this n, forget about root over pi, I'm not interested there. This will be equals to this. And even forget about this x square, right? X square is some parameter alpha which is positive. Don't worry about it, because limit in any case I'm writing over tends n only. Limit in any case I'm finding over n only. So forget about this x square also. Okay. Now try to find me what will be the limit. You can clearly see that. This is how the functions would behave. So for example, if I'm saying about e की power x square, and in fact here you have some parameter positive also. So this is your exponential. This is how your exponential behaves, and this is how your linear function behaves. So exponential rate of growth is way too much than what you can think of. Like for example, if I'm saying how to move this entire thing, I don't know how to move this entire thing. Okay, so if I'm saying that how would your linear function behave? So you will say my linear function would behave this way, and I'm saying now focus upon this particular function. This will be like very rapidly moving functions. It will go as large as possible. However, if you see that rate of growth of exponential will be very larger than the rate of growth of the linear function. In fact, if you simply differentiate it, the rate of growth of the linear function is just a constant 1. And the rate of growth of this particular function is enormous. If you differentiate with respect to n, so you'll get, this is the derivative. Now you can clearly see that as your function, as your x tends to infinity, it will tend towards infinity. So I'll give you an example. Let's say if I'm saying my x is 10 की power 12. So how would your function fx would behave? Fx would be 10 की power 12 because fx equal to x. If this is your function, linear function is there. Agar x को 10 की power 12 your fx would come as 10 की power 12. But function gx, which is like e की power some constant, you can take x square as some constant. Let's say if it is 4, and if I'm writing x, so your g x 10 की power 12, sorry, g 10 की power 12 would be e into 4 into 10 की power 12. Now here you see this is an enormously higher value than this. Overall, you can expect this particular limit to go towards it. Or otherwise, if you're not very much comfortable with what I'm writing or what kind of physical insight I'm giving you, you can just take a L hospital rule, differentiate above and below, and you will find the values. So if you take a derivative with respect to n above, derivative with respect to n below, you will get this. And as n tends to infinity, this is infinitely large, so overall it will go towards zero. So how does this limiting behavior of family of Gaussians behave? So family of Gaussians are there. You can see that x equals 0, at x equal to 0, this could be 1, n tends to infinity, this could be infinity. And if x is not equal to 0, then this will be a non-zero term, infinitely large in the denominator. Overall, this particular term will become 0. So you can easily verify yourself that this particular function or this particular family of Gaussian, if in case I'm constructing the limiting behavior, this limiting behavior corresponds to the Dirac delta function. Is that clear to you? या नहीं समझ में आया? लेट मी नो फटाफट से. फिर कोई नहीं बोल रहा है. अल्पना समझ में आया?
हाँ भैया.
मोहित समझ में आया?
यस.
ठीक है, बोलते रहो यार. ठीक है. So another condition that you had seen was to fulfill the condition that the area under spike should come as 1. Okay, so area under spike should come as 1. So let us see if that area comes out as 1 or not. This is your family. This is your one Gaussian that I'm writing, e to the power n square x square. Some constants were there, and probably this is quite required, but otherwise it will not be right thing to do. So what I would do is I would simply try to write a few things, and you will see as. अच्छा, एक चीज तुम्हें पता होनी चाहिए, otherwise you will not be able to do. 0 to infinite e की power of minus of x square dx. This comes out as root over pi upon 2. This is this I will let you know lately, but right now you just remember this particular integral. Is that clear? And there is, I think there is an issue which I have made, n upon root over pi. Sorry, my mistake. My mistake. Okay. Okay. So this is how it is. N upon root over pi. Okay. Now let us find the integral minus infinite to infinite n upon root over pi. Then you have e to the power minus n square x square. Then you have dx. Now you should take some kind of thing, like let's say okay. Now if instead of this variable x, if I write nx, if I take nx as equals to some, I think y, how would this be? This will be e to the power of, I think, n dx. Okay, this n dx would become dy, isn't it? So you just take this n and dx as dy. So here I'm writing dy, and you take this as y square. And if your n is a positively large, even if it is a positive number, this will become minus infinite to plus infinite. This will become plus 1 upon root over pi. Is that clear? Is that clear? This is an even function,
Yes,
so you can write 2 upon root over pi, and you can write 0 to infinite e to the power minus y square dy. And if integrated, I think this I have already written root over pi upon 2. Root over pi upon 2 into 2 upon root over pi 1. So area under this Gaussian spike, even as n tends to infinity, would be 1. Even as n tends to infinity, this area under this Gaussian spike would be 1. Is that clear to you? So overall, this family of Gaussian, the limiting behavior of this family of Gaussian represents your Dirac delta function. Is that clear? Because it performs all the properties. It performs all the properties. The property number 1, it should have a peak at x equal to 0. Yes, it had a peak at x equal to 0, and that peak was infinitely large. For all those points which are not at x equal to 0, it was 0. You can clearly see I have taken a limit over here, and also that the area under the spike is equal to 1. So this is, I'm just giving you motivation because this is the first lecture for you for all Dirac delta function. That is why I'm doing it. Otherwise, I'll come directly to the point. Okay. Then you can also represent it using family of Gaussians, a family of Lorentzians. So all those people who are doing research right now must be aware of all these terms like Gaussians, Lorentzians, pseudo-Weigelt functions. So all these things are quite normal to people who are doing research because they have to fit the data somehow with Gaussians, then Lorentzians, and pseudo-Weigelt functions, which contains both Gaussians and Lorentzian, all those stuff. Okay, now let us just try to write this also, Lorentzian. So if I just try to write a Lorentzian pulse would be defined as I will have to write some some, you can say, normalizing constants or this way. Now just try to think over this function. Now again there will be two cases. If I try to find the limit of this function, then I should say that what happens if x equal to 0 and what happens if x is not equal to 0. So if x is equal to 0, then this particular term will get nullified, and all over as n tends to infinity, this will become an infinity large thing. See, n tends to infinity, this will become infinity large. And if your x is non-zero, you have some n square term in the denominator. Here it is a linear term in the numerator. Overall, the denominator term will be very large as n tends to infinity, and overall it will become 0. Now, anybody, if he's sleeping or she's sleeping, may ask me, why are we doing this limit? Again, I'm telling you time and again, I am trying to write the Dirac delta function in terms of sequence of functions. First thing, understand. And these sequence of function in the limiting case may behave as a Dirac delta function. This is what is our strategy. Why I am doing this? Because Dirac delta function, as such, we don't know. I mean, such functions we don't know in our calculus of 10th class or 12th class, whatever the last class you had in calculus. So you don't know any such function that it has infinite value at a point and non-infinite zero value for all other points. So we are trying to construct some sequence of functions whose limiting behavior would ideally correspond to a Dirac delta function. So that is why I'm trying to find the limit as n tends to infinity. Time and again I'm doing this, so don't get confused. So at x equal to 0, because जैसे तुम यहाँ लिमिट लेने की कोशिश करोगे n tends to infinity पे, तुम्हारा पहला क्वेश्चन होगा what about this? If x is equal to 0, there is no point writing this particular thing. So if x equal to 0, this will become 1, 0. 1 plus 0 is 1. Overall, n tends to infinity, this will become infinitely large. But if x is something, even as small as possible, this term will in any case remain. And this term, if in any case, if it remains, so denominator has a power 2 in n, and numerator has a power 1. If you take an L hospital thing also, and otherwise also you can think there's an n tends to infinity, this will dominate it will give you a very dominatingly higher higher value, like infinitely large value as compared to the numerator. So overall, this term will go to 0 if x is not equal to 0. Okay, so this is again a sort of a function which you can say that the limiting case of these family of Lorentzian would behave as if it is a Dirac delta function. Okay, now let us come back to the point and let us try to see whether these family of Lorentzian give you a unity, as their area. So if I have to find an area under these family of Lorentzian, how would I do so? I would do so by finding this particular integral, that is n upon pi 1 plus n square x square dx, and I think this would be n upon pi, and I would write integral from minus infinite to plus infinite, limiting value n tends to infinity. Okay, I should absorb this n, otherwise it will make my life slightly difficult, so I'll keep it here. 1 plus n square, I think there was x square, and this was dx. So I'll keep nx as some y again. So this will be limit n tends to infinity, 1 upon pi, and then you have minus infinite to plus infinite. You can take n dx as dy, and you have 1 plus y square, and this will be equal to 1 upon pi, and this will be equal to tan inverse y from minus infinite to plus infinite. Plus infinite, tan inverse infinite would be pi by 2, minus infinite minus pi by 2, this will be pi, 1 upon pi into pi will be 1. So area under these family of Lorentzian, even as n tends to infinity, remains 1. So in the limiting case, these family of Lorentzians would behave in a Dirac delta manner because one, that it assimilates in itself a definition of the Dirac delta function in the limiting case, and further you can see the area under this family of Lorentzian would come as 1. So family of exponential, family of Gaussians, family of Lorentzian. I'll come to that rectangular pulse positive side also, but I was stuck in a property, that's why rejected that kind of thing. And moreover, it does not show you something that I want to assert later on. So that is why I removed that case. I'll take that case shortly. So rectangular sequence of rectangles also, you can see all these different functions that I'm taking right now are in order to explain you that how to represent your Dirac delta function as the limiting behavior of these sequence of functions. And also understand, as I wind up this lecture, that these are very, very essential to your physics. Okay, so don't forget. Anytime you'll find uh, anytime in further study as I go along, if I find certain you can say limiting behavior of these functions, I would directly write them Dirac delta function, and then you will be all the more perturbed as to what I'm doing. So that is why I'm saying please pay attention to this lecture. Okay, so this winds up our lecture. I'll join you in the next lecture.